calculate the projection of vector u onto vector v and the scalar component of vector u onto vector v for the given vectors u and v. So here, let's start by recalling that the projection measures the amount of a shadow one vector casts onto another. And we can calculate our projection of vector u onto vector v by thinking about it as the length multiplied by the direction. And if we think about this visually here, let's say we have some vector v, and we'll say here is our vector u. So from the terminal point of vector u, we can drop a straight line down so that it intersects vector v at a right angle. So the projection of u onto v has the same initial point as both u and v, and it's the vector to that right angle. So this here is our projection of vector u onto vector v. So in calculating this, the length here is defined as the dot product of u and v divided by the magnitude of vector v, and the direction, this is a unit vector in the direction of v. And our first component here, this length is what we call the scalar component of u. Of vector u, and this is specifically onto vector v. And again, this here we recognize as a unit vector in the direction of vector v. So when we're calculating here, when we're asked to find the projection, we'll use the formula, the projection of vector u onto vector v. So that is the dot product of vector u and v divided by the magnitude of vector v squared times vector v, and the scalar component of vector u onto vector v is equal to vector u dot v all by the magnitude of vector v. So these are the two equations that we'll be using here. Right, again, we have vector u, which is u sub 1, u sub 2 is negative 2, 1, and our vector v is v sub 1, v sub 2, which is given to us as negative 3, 4. So let's find the, we'll find our scalar component first, since we need it to get the projection. So looking at our equation, we need the dot product here. So I have vector u dot vector v is negative 2 times negative 3 plus 1 times 4, which gives us 6 plus 4, or 10. And then we're also going to need the magnitude of vector v, and that is the square root of negative 3 squared plus 4 squared, all under the square root. So that's the square root of 9 plus 16, under the square root of 25, which simplifies to 5. So using this, we have, therefore, our scalar component of vector u onto vector v is equal to 10 by 5, which simplifies to 2. And now we can use this here to help us find the projection. This is the projection of vector u onto v, vector v. Okay, so we already know the dot product from the scalar component. We have the magnitude of vector v from our scalar component. So we also know that we're going to need, for the projection here, we need to have the magnitude of vector v squared, or 5 squared, which leaves us with 25. And now we're ready to calculate the projection. So you have the projection of vector u onto vector v, which was that dot product of u and v, divided by the magnitude of vector v squared. And this is a scalar here, all multiplied by the components of our vector v. So our dot product is 10, divided by the magnitude squared, which is 25, times the components of vector v, negative 3, 4. And we can simplify here. We know that both 10 and 25 are divisible by 5. So 5 goes into 10 2 times, and 5 goes into 25 5 times. So we have the projection of vector u onto vector v. In its scalar multiple notation would be 2/5 times the vector negative 3, 4. And then if you wanted to rewrite this in its component form, we can distribute that scalar multiple through to both terms, leaving us with negative 6/5, 8/5. So either answer is beautiful.